Have you ever stopped to think about the weird little quirks in how we talk? The secret rules that we all seem to follow, but nobody ever taught us? Well, today, we're going to dive deep into phonology, the hidden operating system in your brain that organizes every single sound you hear and speak.
And it all kicks off with this simple puzzle. We all learn to write have to, but when we actually talk, it almost always comes out as have to. So what's the deal? I promise you, this isn't just lazy speech or a mistake. It's a perfect example of a deep, unconscious rule that your brain is following, and by the time we're done here, you'll know exactly what's going on. To crack this case, we first need to get one huge distinction clear. On one hand, you've got phonetics. Think of this as the raw, physical reality of sound, the actual sound waves coming out of your mouth. But on the other hand, you've got phonology. This is the abstract system your brain uses to sort all that raw data into neat little categories. It's the difference between the messy real world and the clean, organized file folders in your mind.
Okay, so let's start with that mental system. We're about to explore the hidden logic, this unconscious set of rules that you, me, and every other English speaker follows without even thinking about it.
So what is phonology officially? It's really all about the systems and patterns of sounds. See, it's not about the nitty-gritty of how your tongue physically hits your teeth. It's about how your brain understands that sound as being part of a bigger system. It's like the mental blueprint for language.
And why do we need this blueprint so badly? Because the actual sounds we make are all over the place. Just think about it. You can understand someone talking really fast or really slow. You can understand someone with a completely different accent, a friend who's tired and mumbling, or a kid who's super excited. Phonology is the amazing piece of software that lets your brain hear all those wildly different physical sounds and go, yep, that's the same word. It finds the pattern underneath all the noise.
So how does the brain actually build this amazing system? Well, like any good system, it starts with some basic, fundamental building blocks. And the most important building block of them all is something called a phoneme. The easiest way to think about a phoneme is like a single Lego brick of sound. It's the absolute smallest piece of sound that can actually change what a word means. And you'll always see them written between these slash marks. That's just how we signal that we're talking about the abstract mental category. Here's a super clear example. Take the words pat and bat. They are completely identical, except for that very first sound. The tiny difference between the p sound and the b sound is the only thing that changes the meaning. That one little swap creates a totally different word, which is how we know for sure that p and ba are two separate phonemes, two different Lego bricks in English. And it's the exact same idea here, vine versus fine. The only thing that's different is that first sound. One is a V, the other is an F. And since swapping that one sound brick gives us a whole new word, we know that V and F are also separate phonemes in our brain's inventory. Pretty simple, right? Okay, but here's where it gets really, really cool. It turns out that those mental Lego bricks, those phonemes, don't actually sound the same every single time we use them in the real world. These different physical versions are called allophones. So an allophone is just a slightly different pronunciation of the very same phoneme. And here's the crucial part. Swapping one allophone for another will never change a word's meaning. It might sound a little different, maybe like someone has a different accent, but the word itself stays exactly the same. Let's use one of the most versatile phonemes in English as our guinea pig, the good old T sound. In our brain, it's just one thing, one single category, one idea of a sound. But when that idea comes out into the real world, it can wear a bunch of different hats. Seriously, try saying these words out loud and really pay attention to what your mouth is doing on the T sound. In tar, you get this little puff of air, t. But in star, that puff of air completely disappears. It's just a plain old t. Then you get to water, where it becomes this super quick flap, that honestly sounds a lot like a D. And at the end of a word like cat, you might not even release the air at all. That's four totally different physical sounds, but your brain just files them all neatly under the same mental phoneme, t. Wild, right? Okay, so we've got our sound bricks, the phonemes, and we know they have different real-world versions, the allophones, but you can't just stick them together in any random order. Just like grammar has rules for building sentences, phonology has rules for building sounds. These rules have a fancy name, phonotactics, and every single language has its own unique set. It's the reason a word like street sounds totally normal to an English speaker, but a word that starts with, say, BN or TL just feels wrong. It violates the rules. Your brain knows on some deep level that a word like bnik just isn't a possible English word. A lot of these rules are based on the structure of a syllable. And it turns out pretty much every syllable in every language has this fundamental structure. It's got a nucleus, which is almost always a vowel. That's the core, the heart of the syllable. Before that, you can have consonants, which we call the onset. And after the nucleus, you can have more consonants, and that's the coda. Let's just look at our example, street. It's one syllable, and we can break it down perfectly. The stir sound cluster at the beginning, that's the onset. The long E vowel sound in the middle, that's our nucleus, the heart. And that final T sound, that's the coda. Every word you know is just built from syllables that follow this kind of structure. Okay, now we have all the pieces. We've got phonemes, we know they have different versions, and we know there are rules for combining them. Now we get to see what happens when these sounds start bumping up against each other in fast, casual speech, which, you guessed it, is going to bring us right back to our opening mystery. This brings us to a really important process called assimilation. This is what happens when one sound starts to become more like a sound that's right next to it. And why does this happen? Honestly, it's all about efficiency. Our mouths are basically lazy. It's just easier and faster to make two sounds more similar to each other than it is to make two very different sounds back to back. And with this one idea, we can finally solve the have to mystery. So the word have ends in a V sound. Now, if you put your fingers on your throat and make that sound, v, you'll feel your vocal cords buzzing. That's what we call a voiced sound. But the very next word, to, starts with a T sound. Try making that sound. T. No buzzing, right? That's voiceless. So to go from a vibrating V to a non-vibrating T takes a little bit of extra work. So what does your brain do? Assimilation kicks in. The V sound basically gets ready for the voiceless T that's coming, and it becomes voiceless itself. And what's a voiceless version of V? It's an F sound. And boom, there you have it. Have to becomes have to. And assimilation isn't the only shortcut our brain takes. Another really common one is elision. That's just a fancy word for deleting a sound completely to make things easier. For example, we almost never actually say the D in friendship. It just becomes friendship. Again, it's not lazy, it's just a super efficient, rule-based process that happens automatically. So, after all that, let's zoom out. What's the big picture? Why does this hidden system of rules and mental categories actually matter? Well, it matters because phonology is what makes spoken language work so incredibly well. It is the invisible software that's constantly running in the background, translating all those messy, variable physical sounds from the real world into clear, meaningful ideas. It's what lets us talk fast and take shortcuts and still understand each other perfectly across all those countless variations in how we speak. And that leaves us with a pretty fascinating final thought. We've just seen how our brains are constantly, automatically working behind the scenes to streamline the sounds of our language. So it really makes you wonder, what other incredibly complex systems are our minds simplifying for us every single second of the day in ways we haven't even begun to notice? Thanks for tuning in.